Welcome to AI Tech Book, your certified AI architect prep. Domain 1, Agentic Architecture. Today, the question every architect faces, multi-agent or single agent, and when multi actually wins. Two teams, two builds, two mistakes from exactly opposite directions. The first team wires one powerful agent to a research question, the kind that needs 200 sources across a dozen complex tools. The agent serializes every step. It overflows its context halfway through. It returns something shallow. One context window wasn't enough for this work. They needed many. The second team sees a demo of multi-agent orchestration and fans out to a fleet for every query, including the simple ones. The token bill comes back at 15 times. A normal conversation. Quality is unchanged from what one agent would have done. They paid for capacity they never needed. Same question from both sides. When does multi actually win? Three criteria decide it. And one mechanism explains why all three are true. Anthropic's engineering team built a production multi-agent research system and they're specific about when the architecture earns its overhead. Three conditions. Heavy parallelization. If your task fans out into independent subtasks that can run simultaneously, each in its own thread, each returning a result to a coordinator, that's the first green light. The work has a shape that fits parallel execution, exceeds one context window. Some tasks genuinely need more information than any single. Context can hold hundreds of documents, dozens of sources, data that would rot a single agent's window before it reaches a conclusion. When the information volume exceeds one context, you don't make that context bigger. You make it plural. Many complex tools. Some tasks require interfacing with a large number of sophisticated tools, databases, code executors, web search, APIs, file systems, and routing them through. A single agent creates bottlenecks and bloat. Scoped workers, each with only the tools they need, are cleaner and safer. Those are the three criteria. But here's the mechanism behind all of them, and this is the part that changes how you apply the rule. Each worker agent runs in its own fresh conversation. Watch what this means. Intermediate tool calls, file reads, search results, intermediate reasoning, all of it stays inside the worker. Only the worker's final message returns to the coordinator. The parent receives a concise summary, not every file the worker read. This is context isolation. The win isn't that you're running things in parallel, though you are. The win is that each worker has a clean desk, none of their work floods anyone else's context. The wall between agents is the win. That isolation is why the Claude research team measured a 90.2% lift when they built their multi-agent system using Opus 4 as the lead end. Sonnet 4 workers on a research evaluation. That number belongs to that era system, and the evil task was specific, identifying board members across hundreds of companies. But the mechanism producing that lift is the same one you're looking at now. Heavy parallelization. Exceeds one context. Many complex tools. Three green lights. Each one maps directly onto the isolation mechanism that makes distributed context windows produce better output than one overloaded window. Now the two red lights, the shape of work where multi-agent actively breaks, and the cost gate that should stop you even when the shape looks right. First red light, shared context. Anthropic states this directly. Domains that require all agents to share the same context or that involve many. Dependencies between agents are not a good fit for multi-agent systems today. Think about what that means in terms of the isolation mechanism. Each worker gets a clean, fresh context. That wall is the architecture's core feature. But if your task requires every agent to know what every other agent is doing, you're fighting that wall. The architecture's strength becomes its constraint. Tightly coupled logic changes in a code base are the named example. Most coding tasks involve fewer truly independent subtasks than research does. And this is worth being precise about. Claude's Opus 4.8 launch does highlight code-based scale migrations with hundreds of parallel workers. That isn't a contradiction. Large migrations decompose into independent file and module units. Each worker takes one file, one module, no shared state. That's the parallelizable subset of coding. It fits the first green light. What doesn't fit is a logic change where every function depends on every other. Match the criteria, not the domain name. Second red light, economics. Multi-agent systems use about 15 times more tokens than a standard chat. A single agent already uses about 4 times more. That multiplier isn't a bug. It's the cost of running fresh context in parallel. Each worker's clean desk has a price. The economic gate: use multi-agent only when the value of the outcome outweighs that expense. A query that one agent answers well in 2 minutes doesn't need a fleet. A research task that would overflow one context and return something shallow with an outcome your business depends on, that's exactly where 15 times the cost earns its return. One rule covers the exam question and every real system design decision. Multi-agent when the tasks are independent. One agent when they share state. If the work fans out in parallel, exceeds one context window, and calls many complex tools, and those tasks don't need to know about each other, multi-agent is structurally correct. The isolation mechanism earns its cost. If the work requires shared state, tight sequencing, or agents that depend on each other's. In flight results, single agent, you're better served by one clean context running the full task than by multiple contexts that need to communicate through a bottleneck. Size the fleet to match the task. Here's the scaling heuristic from the Anthropic research team. Simple fact-finding calls for one agent with 3 to 10 tool calls. Direct comparisons work well with 2 to 4 workers, 10 to 15 calls each. Complex research, the kind that needs clearly divided responsibilities across independent subtasks, that's where 10 or more workers earns its overhead. Embed these sizing rules in the lead agent's prompt, and you prevent the worst failure mode. A lead that spawns 50 workers for a question one agent could answer in seconds. 2 things to carry out of this. First, the 3 good fit criteria all have one underlying reason: context isolation, fresh windows, independent work, summary not pile. That mechanism is why multi-agent wins. On the right shape of task, it's not about more agents, it's about more clean contexts. Second, the 2 bad fit conditions are the same mechanism seen from the other side. Shared context means you're trying to tear down the wall the architecture built. Heavy dependencies mean the wall becomes a bottleneck instead of a feature. The wall between them is the win, unless your task needs to tear it down, which means you needed one agent from the start. On the exam, task shape decides, not task size. Parallelizable, context exceeding, tool heavy, multi-agent. Shared state, tightly coupled, single agent. The 15 times cost caveat flags the economics question. The coding reconciliation, independent file units are parallelizable, catches the nuance case. For a deeper look at how multi-agent systems actually break in production over spawning duplicated work, errors compounding across long runs, that's Atlas Episode 7. The decision criteria you just learned are the first half of the D1 picture. Multi-agent wins when the task is parallelizable, exceeds one context, or needs many. Complex tools, and breaks when the work shares state. Task shape decides, not size. If this sharpened your judgment, subscribe to AI Tech Book, one exam topic every day. Next, task decomposition, breaking a goal into scoped subagent tasks.